All right, so this video is going to look at stoichiometry involving aqueous solutions. When you're dealing with solutions, you're going to have to, in stoichiometry, you need a balanced equation, and you also are going to need to find a way to get moles to relate the reactants to each other or to products or vice versa. So first thing you want to do is make sure you have that balanced chemical equation, and then you want to be able to determine how much of the reactants you have. I have grams on here, but moles is probably what you're going to be ending up going to. If you're given grams, you would convert it to moles. If you're given a molarity and a volume, you would use that to find your moles. You then need to figure out what is your limiting reactant if you have information about both reactants that are involved. One of them is going to get consumed more quickly than the other, just like we talked about with limiting reactants earlier on this part of the unit. So you are going to use stoichiometry to determine which reactant is going to be used up completely first. And then once you have that information, you can use your limiting reactant to determine how much of the other reactant you would need to have, or how much product could be made based on that limiting reactant. So here we're taking Na3PO4 0.1 molar. We want to know what volume of it would be needed to precipitate out all of the lead 2 ions from 150 mils of 0.25 molar PbNO32. So we know PbNO32 and Na3PO4 are going to react together, and we know that Pb is going to be precipitated out, the Pb ions, with the phosphate ions. So sodium and nitrate are going to go together as well. And if you go through and write your formulas and you balance out your equation, this is what you should see. 3 PbNO32s plus 2 Na3PO4s make 6 NaNO3s and 1 Pb3PO42. So I want to figure out which reactant is limiting, and I only have the information to find moles about one of my reactants, the PbNO32, so that has to be my limiting reactant. I would take its volume and its molarity to find its moles. And now I can use stoichiometry to figure out about Na3PO4. If I want to find the volume of 0.1 molar Na3PO4, I need to have moles so that I can use moles and molarity to help me find volume. So I'm going to start with my limiting reactant, the 0.0375 moles. I didn't talk about sig figs up there, but your volume had 4, your molar mass had 3, so you would want 3 in your answer for the first part. I'm going to use stoichiometry to convert from moles of PbNO32 to moles of Na3PO4. And based on the balanced equation, I see that the coefficients for those are 3 to 2. The moles of PbNO32 are going to cancel out. I'm going to take that 0.0375 number, double it, and then divide it by 3. And that gives me 0.0250 moles of Na3PO4 are actually consumed in this reaction. Again, we're not done yet because we want to find volume. We have moles and we have molarity. So we're going to take those two pieces and divide them into each other so that we can get our volume in liters. And when you do that, you get a volume of 0.250 liters or 250 milliliters. So our second question is going to have information about both reactants, and we're going to use those to find out about our product. We have 100 mils of 0.1 molar barium chloride that's mixed with 100 mils of 0.1 molar iron 3 sulfate. And then we want to know what's going to be left over, what ions are going to remain in the solution. So I need to write a balanced equation first between barium chloride and iron 3 sulfate. I think when you write that balanced equation, you're going to see that barium and sulfate make a precipitate. And so when I balance it, I'm going to need 3 of the compounds containing barium and 2 of the product that contains iron. I'm going to use the information I have for each of my reactants to find their moles. So I'm going to take the volume and the molarity of barium chloride and the volume and the molarity of iron 3 sulfate to get my moles for both reactants. At this point, I'm going to use stoichiometry, my balanced equation, to relate moles of barium chloride and moles of iron 3 sulfate to a product. It really doesn't matter which product I pick. However, since the question asked me to find the mass of barium sulfate, I'm going to go ahead and convert from the moles of barium chloride and the moles of iron 3 sulfate to grams of barium sulfate. just get it over with. So moles always gets 1 times its coefficient. The grams of barium sulfate gets its molar mass times its coefficient. When the moles of barium chloride cancel out, you're left with 2.33 grams, and that fits for our sig figs, 3 in our moles and 5 in our molar mass. So the second part, we're going to take the moles of iron 3 sulfate and we're going to set up that conversion. Well, the problem with this one is that we only have 1 mole of iron 3 sulfate being consumed for every 3 moles of barium sulfate, so we can make much more barium sulfate from the iron 3 sulfate. What that tells me then is that the barium chloride is acting as my limiting reactant, and it is the barium chloride that is going to determine how much barium sulfate I can make, 2.33 grams. And this question I ask you is the same question before, but this time, what ions would remain in solution? Well, there's 4 ions present: barium, chloride, iron 3, and sulfate. We know that all of the barium went into making barium sulfate, so there is no possibility of any barium ions being left in solution. They were completely used. We know that our spectator ions were still present, they just were dissolved, they were diluted a little bit more. So the chloride and the iron 3 are going to be present just in the diluted volume that we have seen. Sulfate, however, was part of the excess reactant used to make the precipitate, and because sulfate did not get completely used, it too would be present in our final mixture. And then we would also obviously have our precipitate as well, the barium sulfate.